Hi dear friends, good morning to one and all. Dear friends, in the last part of the video, we discussed about the quantum chemistry, and in that lecture we discussed a lot of things regarding with the quantum mechanics or the basics of quantum chemistry. Dear friends, today in this part of the video we are going to discuss a new topic which is a very important topic in the field of chemistry, particularly I will say in the field of organic chemistry, in order to predict the correct structure of the molecule known as or entitled as the nuclear like microspectroscopy, IR spectroscopy, UV spectroscopy, then Raman spectroscopy, and this is another type of the spectroscopy which is entitled as a nuclear magnetic resonance spectroscopy. Dear friends, today in this part we will discuss about some introductory part of nuclear magnetic resonance spectroscopy and how the molecules or the different types of the species show the nuclear magnetic resonance spectroscopy whenever these are exposed to electromagnetic radiation. Dear friends, as you all are aware about the structure of the atom, that it consists of the two parts, particularly the central part that we call it as the nucleus, and the other part which is present outside the nucleus that we call it as the extranuclear region. Dear friends, also we are aware about the particles which are present in the nucleus and the particles which are present outside the nucleus. Today, dear friends, we are going to talk about the response given by the particles which are present in the nucleus, or we will say the response given by the nucleus of the atom whenever it is exposed to different or the particular type of electromagnetic radiations. So here these responses of the nucleus whenever it is exposed to electromagnetic radiations are studied in the branch, and that branch is called as the NMR spectroscopy, or simply it is called as the nuclear magnetic resonance spectroscopy. Dear friends, as far as concerns the nucleus, then this nuclear magnetic resonance spectroscopy involves the change in the spin state of nuclear magnetic moment. It involves the change in the spin state of nuclear magnetic moment whenever nucleus absorbs electromagnetic radiation in presence of applied magnetic field, and whenever nucleus absorbs the electromagnetic radiation means nucleus absorbs the energy from the electromagnetic radiation, then definitely it shows the change in the state from low energy level to the higher energy level. Again, if we'll talk about the nucleus, then you will come to that there are different types of the nucleus on the basis of their spin, and the nucleus or the nuclei which are possessing or which are having the spin are called as spin active nuclei, and these are the nuclei which can show the NMR spectroscopy, and the nuclei without nuclear spin are called as the spin inactive nuclei, and the spin inactive nuclei do not show or do not give the NMR spectra. So this is very so for the NMR spectra the nucleus must have the spin, otherwise it will not show the spin. This is one of the important basic thing regarding the NMR spectroscopy. Which nucleus or the which nuclei will show the NMR spectroscopy? Those nuclei which are having the spin, that nuclei can show the NMR spectroscopy, others do not. If the preceding nuclei irradiated or exposed to electromagnetic radiation of desired frequency, then what happens that I already told you, then the nuclei will absorb the energy from the electromagnetic radiation, and it will move from lower energy level to the higher energy level. So this is very important thing, and the change in the energy level of the nuclei will be responsible for the NMR spectroscopy. Then the energy associated with the frequency, energy associated with radio frequency is incapable of disrupting even the weak chemical bond in the molecule also. So these radio frequency are responsible for the NMR spectroscopy for the change in the state of nuclear spin from one energy level to the another energy level, from lower energy level to the higher energy level. So these radio frequency are responsible for the NMR spectroscopy. So here for the NMR spectroscopy, the spin of nucleus is very important. So what is the spin of the nucleus that will decide the type of or the nature of NMR spectroscopy or the NMR spectra, and that's why it is very essential to calculate the nuclear spin of the given nuclei. And in order to calculate the spin of the nuclei, there are various rules which can be used here. And as we are all are aware about the structure of the nucleus, and the nucleus consists of the two particles, particularly one is the proton, another one is the neutron, and we are also aware about the charge present on the proton, that is positive charge, and neutron is without charge. So if both the number of protons and the number of neutrons are even number in the nucleus of the atom, if both are, means proton and neutron both are the even number like 2, 4, 6, then the nuclear spin of such a nuclei will be 0. And the examples like helium 4, oxygen 16, carbon 12, calcium 40, all these nuclei are having the odd number of proton and the odd number of neutron. That's why their nuclear spin is 0, and these nuclei will not show the NMR spectroscopy. Again, the another rule here, if the any nuclei containing both odd number, it means that it consists odd number of protons and the odd number of neutron, then such nuclei will possesses the integral spin. Integral spin means its spin will be a whole number like 1, 2, 3, or like there is nothing but simple case. So that we will discuss. And the example of the nuclei which are having the integral spin number, and this hydrogen 2, lithium 6, boron 10, nitrogen 14. I hope you can you are able to predict the significance of this number. So these bottom numbers indicates the atomic number, means it indicates the number of protons. These 2, 4 top figures indicate the number of proton and the number of neutron, because it is the mass number. So this 2 indicates the sum of proton and the neutron. The difference between these two, top figure minus lower one, so that is superscript minus subscript, indicate the number of neutron. That's why here in all these 4 nuclei, number of proton is also odd number and the number of neutron is also the odd number. That's why these nuclei will have the integral spin. Instead of this, if either the number of proton or the number of neutron, either of these two in the nucleus is odd, means either the number of proton will be odd or the number of neutron will be odd, the another one will be even, then the nuclei will possess the half integral spin. Half integral spin, and this is in the fraction 1 by 2, 3 by 2, 5 by 2, like this. And there are two nuclei which are having the half integral spin. Another first one is the hydrogen 1 and another one is the carbon 13. So these are the two. Dear friends, I have one table here which can indicate the number of neutrons and the proton present in the nucleus along with their spin number with their example also. So here this column indicates the number of protons, it indicates the number of neutron, and they based upon number of proton and number of neutron, their spin number will be here along with their example in this column. So if both are the even, the spin number will be 0. Already I told you the example. If number of proton is odd, the number of neutron is even, then their spin number will be 1 by 2. The examples of hydrogen 1, nitrogen 15. If both are the odd number, then already I told you the spin number will be integral value. This is integral value 1, whole number. So example hydrogen 2, nitrogen 14. If this is the even, number of proton and number of neutron will be odd. Again, this is nothing but the 1 by 2. Carbon 13 is the example. If this is the odd and the number of neutron will be even, like in this case, but here definitely it is the fraction, that is 1 by 2, and here it is 3 by 2. One example is the boron 11. So this table indicates the different number of different types of nuclei having different number of proton and the neutron along with their spin number and the examples. So dear friends, in this case, as one thing should be clear you, actually here nucleus is going to take active part in the NMR spectroscopy. Rather nucleus, I will say the nuclear particles are taking a role in the NMR spectroscopy, and that's why we are well known about the particles which are present in the nucleus, that it contains the two particles proton and the neutron, and that's why the nucleus will have the charge due to the proton, that it has the positive charge. So charged nucleus regarded as the spinning sphere. So this charged nucleus of the atom always considered as the spinning sphere, which generates magnetic field like an electric current flows in the coil of wire. So hence the nucleus is associated with the nuclear magnetic moment, as this spinning nucleus generates magnetic field, and the strength of this magnetic field indicated by means of an mu. So the nucleus which is associated with the nuclear magnetic moment mu along the axis of spin, the spinning nucleus acts as the small bar magnet, and the axis of which is coincident with the axis of spin. Therefore, the nuclear magnetic moment for the proton, because it carries nuclear charge, is because of the proton, and that's why the nuclear magnetic moment for the proton is called nuclear magneton. So this is the nuclear magnetic moment of the proton in the nucleus, called as nuclear magneton. It is always expressed in terms of Tesla. It is always expressed in terms of unit Tesla, and it is indicated by the symbol mu, which is given by the equation mu is equal to Eh upon 4 pi into mass of proton. Here is the electronic charge, S is the Planck constant, Mp, this is the mass of proton. By putting all this value, we will get the nuclear magnetic moment of proton, mu is equal to 5.05 into 10 raised to minus 27 joule per Tesla. So all atomic systems have nucleus at the center with electrons present in the extranuclear region around the nucleus, and the nucleus contains, already I told you, proton, the neutron. Hence the nucleus is positively charged species. Though all nuclei are positively charged, only some of them possess a spinning property. It means that all nuclei do not have the spin. Only of some nucleus can show the spinning property, and the spin characteristic of nuclei are defined in terms of number. The spinning property of nuclei are defined in terms of number, known as spin quantum number, indicated by means of an I, and which gives rise to the spin angular momentum of the nucleus. So the magnitude of spin angular momentum of nucleus is given by the equation spin angular momentum. It is applicable to the nucleus, spinning nucleus, and this is always equal to under root of I into I plus 1 into h upon 2 pi. Here this I is the spin quantum number of the spinning nucleus, and h is the Planck constant. So when the spin active nucleus, means those spin quantum number is greater than 0, so they have some value of spin, that's why spin quantum number will be greater than 0. If it is equal to 0, then definitely such type of nuclei are called as spin inactive. So this spin active nuclei, means having the spin quantum number is greater than 0, are placed in a magnetic field of strength H0. This is the strength of the applied magnetic field. Then the nuclei take up various different orientations depending upon the value of spin quantum number. So this is very simple. So whenever such a spin active nuclei are placed in the applied magnetic field, then this spin of the nuclei, the spinning nuclei takes the different orientation based upon the spin quantum number, and for a given value of spin quantum number I, then possible number of orientation, the number of orientations is given by the two into I plus 1. So here for example, a particular nucleus having the single proton, that's why its spin quantum number will be 1 by 2. Okay, then the number of possible orientation will be 2 into I, that is 1 by 2. So it has the two orientation. If any nuclei having the single proton, then the spin quantum number will be 1 by 2. That's why the number of orientation will be 2. So which are these two orientation? That is, one is the plus 1 by 2, another one is the minus 1 by 2, corresponding to their energy plus mu h 0, and this corresponds to minus mu h 0 energy. Instead of this, if the spin quantum number of the given nuclei is 3 by 2, then the number of orientation will be 4. That corresponds to 3 by 2, 1 by 2, minus 1 by 2, and minus 3 by 2. So these are the different orientations of spinning nucleus in brains of applied magnetic field. For example, we will discuss about the proton present in the hydrogen nucleus. So hydrogen has only one proton, that's why its spin quantum number will be 1 by 2. And when such a proton is placed in the magnetic field, then the number of orientations are given by 2. And these two orientations, so it has the two orientation. So one orientation will have the lower energy, it is called parallel align with the applied magnetic field, so it is parallel with the applied magnetic field. And another with the high energy, it has the high energy, it is opposite to the applied magnetic field, or it is simply considered as the anti-parallel orientation aligned against the field. So here it can be shown. So this is the spin of the nucleus in absence of applied magnetic, in absence of magnetic field, and having the orientation 1 by 2, having the only one proton, and so its spin quantum number will be 1 by 2. Whenever it is placed in presence of electromagnetic field, it will show the two orientation. One is plus 1 by 2, that is opposite to the applied magnetic field. Another one is the minus 1 by 2, it is parallel, or it is in the direction of applied magnetic field, corresponding to their energy minus mu h 0 and plus mu h 0, and their energy difference will be 2 into mu h 0, that is simply higher minus lower. Instead of this, if the spin quantum number is 1, then it has the three orientation 2i plus 1, that is plus 1, 0, and minus 1. And if it has the spin quantum number 3 by 2, definitely it has the 4 orientation corresponding to plus 3 by 2, plus 1 by 2, minus 1 by 2, and minus 3 by 2. Definitely if we compare their energy, definitely this also indicates the order of their energy. Since the parallel orientation has a lower energy, so it will be more stable, corresponding to minus mu h 0 energy, whereas the anti-parallel orientation has the greater energy, that is corresponding to plus mu h 0, so it is less stable. So remember that anti-parallel orientation is always less stable, parallel orientations are always more stable. And the energy difference between these two levels is indicated by means of delta E is equal to 2 into mu h 0. This is the equation that can be used to calculate this. But you know, the energy difference between the two energy levels is always given by the Planck equation H mu. That's why we can equate this equation number 2 and the equation number 3. We will get this equation H mu is equal to 2 into mu into H 0. And for the hydrogen, the spin quantum number is always equal to 1 by 2. And if we'll arrange this equation, 2 will be equal to 1 by 2. And if we'll put this equation in the equation number 4, then instead of 2, we will put 1 upon I. And we will get this equation H mu is equal to mu into H 0 upon I. I is the spin quantum number, mu is the strength of the applied magnetic field, H 0 is the, this mu is the magnetic moment, magnitude of the magnetic moment, and H 0 is the strength of the applied magnetic field, H Planck constant, mu is the frequency. So multiplying these two equations, both the sides of this equation by means of 2 pi, so we'll get this equation. And if we'll arrange this equation, I will transfer this H on this side, so we will get this equation, that is 2 pi mu is equal to 2 pi into mu. This is mu and this is mu, H 0 upon H into I. So for the given nucleus, this 2 pi and mu, this is the magnetic moment, the H, and spin quantum number is also constant. So all this ratio is constant for the given nucleus, and this constant is called as the gyromagnetic constant or gyromagnetic ratio, indicated by some gamma. This gyromagnetic ratio depends on the magnetic moment mu and the spin quantum number of the nucleus. That's why 2 pi mu into gamma into h0. So we can write the equation for the gyromagnetic ratio. Gamma is equal to pi mu upon h0. So here magnet, and if the axis of this spinning nucleus, such a spinning nuclear small bar magnet, is not exactly oriented parallel or anti-parallel with the applied magnetic field due to spinning, then the result is that its rotational axis draw out a circle perpendicular to the applied magnetic field, and this motion of the nucleus is called as the precession. Here I can show you this. Here the expected axis of this is the spinning proton, okay, and the expected axis of spinning should be in the vertical direction. It is either parallel or anti-parallel with the applied magnetic field. But if it is not exactly parallel or anti-parallel, and it shows if this is the axial, then it will draw just of the circle, rotational sphere, and this is called as the precisional orbit, and the nucleus is called a precessing nucleus, and this gives to the nuclear magnetic moment mu. This is the axis of nuclear magnetic moment, and this called as the this is called as precision, and nuclei is called as precisional nuclei. And the precisional angular velocity of such nuclei omega 0 is equal to the product of gyromagnetic ratio and the applied strength of the magnetic field H0. That is given by this equation. Omega 0 is equal to gamma into H0, and this angular velocity omega 0 can be converted to frequency of precision nu 0 by dividing it by 2 pi. So omega 0, whenever divided by means of 2 pi, it will be converted into frequency of precision nu 0. So here omega 0 is equal to already gamma into h0. So we got the equation for this frequency of precision, and the frequency of precision is given by gamma means gyromagnetic ratio into strength of the applied magnetic field given divided by 2 pi, and this equation is the equation for the frequency of precision. So dear friends, in this way we have discussed a lot of things, or the lot of basic things of NMR spectroscopy. We also discussed about the precision nucleus. We also discussed about the different rules which are used to determine the spin of the nuclei or the spinning nuclei, and we also discussed about the condition for the nuclei to show the NMR spectroscopy. So dear friends, in the next part of the video we would like to discuss about the relaxation process, how the high energy nucleus transfer its energy in its surrounding. That process is called as the relaxation process, and we would also like to discuss about the different types of the relaxation process as well as some instrumentation. So we will resume in the next part of the video to discuss about the relaxation process and its types. Thank you very much.